Next up, we have Kevin Marchbank. Kevin is a basic scientist who has had a long interest in complement and the immune system. He trained in Glasgow and then came to Newcastle to start his own lab via Cardiff and Denver. And Kevin's going to talk to us today about the immune system. Thanks, Kevin.
Thank you, David. Thank you, Sally, for giving me the honour and challenge of trying to describe the immune system in 30 minutes. So, I'll dig out my own laser pointer because then I feel at home. Yeah, I'm a scientist. I speak maybe 3 languages. I will try and stick to English today. It's my 3rd language. I would say Scottish first, and then science next, and English last. But I will try and stay in English. So I started with this lovely picture of Newcastle, which is probably like that out there at the moment. This is the Millennium Bridge. And this is the important part of the immune system, and why is it important in the kidney? This bridge will tilt with as little energy as you need to boil a kettle to make a cup of tea. It's in real fine balance, and the immune system's in real fine balance. And when it's pushed the wrong way, in the case of MPGN and C3 you end up with inflammation, so the kidney is on fire, if you like. And that, in itself, leads to the failure of the kidney. The immune system is not necessarily going wrong, it's just going off track. It's lost its balance, it's attacking self, in essence. And so I think this bridge in particular illustrates that. I also think of it as showing the sea of complement, which bridges the older parts of the immune system, and I mean that in the sense of evolution, and the newer parts, the cultured parts. There's the Baltic art there. And so it bridges between the old and the new. So we'll touch on complement a little, but that's for later. We have people who can speak to complement maybe slightly better than I can. I'm here to talk about the immune system. Why do we need it? Anyone? This is supposed to be interactive, so. Go on then. Yeah, so disease, or we'll say pathogens, is another word for disease. These are things that attack us. And did you know that there's nearly 1,500 pathogens that we have to deal with? Maybe not on a day-to-day basis, but fairly often. So there's the bacteria. And of course, we're all pretty familiar with good bacteria, aren't we? Because they're in all these drinks and everything else yogurts, and they're always trying to sell us good bacteria. These are the bad boys. These are the attackers. So this is our enemy. And of course, there's the viruses, and we've all had common colds and flu. Hopefully we haven't had so many of the other ones mentioned here. And then there's things like fungus and parasites. And there's about 3 new pathogens that are discovered every year. So we're still working out all of the bad guys out there. So we need to have a fairly sophisticated defense. Right, so the immune system, it's broad. And I thought, where do we start? And here is one of many terrible graphics that you're going to see. Unfortunately, I don't have the budget that Hollywood does. But so this is it. The first part of the immune system is the barrier defense, your skin. So it's a wall. There's lots of walls. There's Hadrian's walls, not far from here. That's a defense. So it's okay until it's breached. So there we go. Cut yourself shaving. Mostly everyone has done that at some point or other. And that allows bacteria in. And once they're in the bloodstream, they can disseminate. Complement, that comes into it here. So this is one of the first things that complement's good for, is warning us that bacteria is in the blood. But we've also got all these other barriers that most people don't even think about as being part of the immune system. So saliva, tears, mucus, earwax, sweat. All of them have roles in the immune system in the sense that they block the entry of bacteria. I'm going to focus on bacteria. It could be a virus, etc., etc. So, red cells, you've heard about, they're the blood. They're what we see when we cut ourselves. But there are also other cells known as the white blood cells, generally. They come in a couple of types, in fact, many types. But let's break them down into two main classes. So firstly, we have to say that this is us in terms of blood around the body. Here's our kidneys, arteries and veins. You could add on another system, the lymphatic system, but that just complicates things, so let's keep it simple. There's the bacteria they're in. They're not to scale, just in case you're worrying. They get around here. And so this is quite a big area, so we need to have specialized cells, the white blood cells. Here's one. I've stolen this from the BSI website. I hope they don't mind. I thought it was a perfect picture to show a kind of a white cell, and it sniffs them out. So it sniffs out things, and complement helps these white cells to sniff out the bad guys, or bad green bacteria here. And once they've got them, they like to eat them, like Pac-Man. So they'll just munch, 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 munch up bacteria. When they've sensed them and got them, they'll just eat them up. These are known as phagocytes, and I think this is the better picture of a phagocyte. They're pretty good at it, and they're ravenous. They'll just eat their way through these things. So the one thing about these types of white blood cells is they chew things up, and then they digest them, and they think about it, and they stick it on the surface. And one of those cells is a dendritic cell. I'm going to switch my analogies a little bit to this. Anyone tell me what this is? It's an AWACS, yes, command and control. So that airborne command and control, that is a plane that's designed for helping to work out where things are and letting other people know. So that's a particular cell, dendritic cell, that's good at that. And that's important. Now, the other thing about these cells is they don't have much in the way of a memory. They don't remember what they've eaten, they just enjoyed it. I mean, they just keep coming back for more, they'll keep going on and on for more. But they don't remember what it looks like other than it was tasty. So why is memory important? Do we know who this is? That's a toughie, maybe. It's Ed Jenner, and he did an experiment, and he was a GP in Gloucester, I believe. I hope I'm right. Who essentially gave this little child, it wasn't his child, it was the milkmaid's child, cowpox. And by giving cowpox to this child, prevented it from getting the much worse disease, smallpox. Now, these sort of studies aren't allowed today, but this is vaccination. And vacca comes from cow, so vaccination, forced education, and of the immune system. So you're giving it something and telling it that this is bad. But in order for that to be any good, the immune system has to have memory. And these are the cells with memory. So we've got two more planes. Anyone what this one is? Yeah, that's an easy one. That's the stealth bomber. So I've chosen that to represent a cell that's called the T cell. It's very imaginative. I'll come to that in a second. And there is also another a cell called the B cell, which is this plane here, which actually I didn't check what it is, but maybe someone knows. It's like a MiG-29 or something like that. But and this cell, the T cell, is highly specialized, very expensive piece of kit, if you like. And in terms of the body, to make one of these, it's an expensive job. It's just the same as a stealth bomber. Stealth bombers have laser-guided bombs. T cells are a bit like that. They lock on and they can kill cells that have got viruses in them, particularly. B cells, however, they're good at producing antibodies. Antibodies are like missiles. They're launched from, in this case it's a plane here, from the cell, and they go off and they hit the target. So they're more like heat-seeking missiles, if you like. They should lock onto the target. They're designed to do that. And in that case, they label it up for destruction. Now, this is where our dendritic cell pops back into it. So now you can see my whole analogy together. These guys are always in communication with each other. They organize the defense. They have memory. They can remember what they've interacted with. And therefore, they give you the modern immune system, the system that allows us to determine that we've met something before and they're there to respond quickly and get rid of it if it is dangerous. Right, so now we have to go into an important concept of friend or foe. So in any battle, in any war, we need to be able to tell the difference between self and non-self, or friend or foe. So, scary slide. So this is one that I use in my lectures. This is about as complicated as I'm going to get with it. So I said about T cells, this is your thymus. So we invest a lot into generating these cells with memory. We have a whole organ there that is essentially about producing our T cells. So I've switched it to a cartoon here. So this is our stealth bomber. They are a bit like Transformers, so it's allowed to do that. So this is our T cell, and it's coming to the military academy, which is our thymus. So T cell gets its name from thymus cell, yeah. Here it is, going into there. So what's it learning? Well, it's learning what aircraft are friends and what are enemies. Patterns. It recognizes patterns. So just in case, we need to be able to tell the T cell that complement, say C3, is self. We need to say that molecule, that important molecule in the complement system, is self, and we don't want it attacking the complement system, or say C3. But we do want it to attack bacteria, which could be one of them. That could be a bacteria shape. And so in this military academy, our T cells and indeed our B cells go through a similar thing. Learn to tell the difference between foreign, bad, and self, good. So let's do a little bit of immunity in action. Here we go. So our bacteria are in the blood. And the first thing we get are flares. Complement is like a flare, a distress signal. This is bad. This is not good. This bacteria is in our system. I don't like it. There are other types of flares, but we're going to talk about complement. So here's our B cell. It's transformed into this shape so that I can show you it binding to the bacteria. It also says to the dendritic cell, who has a taste as well. And so these guys get together and ask the T cell what it thinks. And they all communicate. And that tells the B cell that, yes, this is bad. And it sends out its missiles, which lock onto the target. And actually, here comes our phagocyte. Here comes our Pac-Man, and eats them up now, because it's been locked on with those missiles. And that's immunity in action. That's us clearing bacteria from the system. So we're all here in this audience. We're all probably fighting things at the moment that we've seen before, and that we're dealing with them, and we don't even know because we have this memory. So once this reaction's happened, we expand these cells, and they go off and live with us for maybe 60, 70 years. We don't actually know how long they live. We know that they do because vaccination works. It can last that long. So the B and the T cells proliferate, go away, and they're there ready to come out. Rapid response team. They're our SAS. They come in and they can deal with the situation fast. That's what they're there to do. Right. So I have to also, to make sense of this a little bit more, I have to also talk about having a steak dinner. Yeah? So what happens there? Now our B cell sees cow, or beef in this case, and it thinks, actually, that looks a bit foreign. That's not like self. The pilots also quite like a steak dinner, so they have some too. And they're not so sure, and they ask the T cell, and he's like, well, I do like steak, but I'm a vegetarian these days. I've moved on. But there are no flares. There's no complement. So in that case, the immune system thinks, actually, no, this isn't foreign. It's not self. It is foreign, but it's not self. I don't know what to do. So it actually just switches itself off. It's still there. It's in the background, but it's not going to respond to this. Of course, people with food allergies, well, that is when things get confused and it does start to attack self, a form of autoimmunity. Right, so I have given you the immune system working exactly the way we want it to, but of course we're here today to talk about the immune system not quite working the way it should do. So this picture is too good to be true, isn't it? That doesn't quite look right and whatever. I've stole it from the web, so I know it's made up. Here we are. So, some of the things that happen in war. We get spies in our midst. And so sometimes, and bacteria have been around as long as we have been, and to be honest, we're made up of a lot of the same proteins that bacteria are made up of. That might be a bit of a nasty thought, but there we are. We're all made up of the similar sorts of things, and the differences are a lot less than we'd like to believe. So here our B cell recognizes it. It is foreign. The dendritic cell recognizes it and quite likes the taste of it. There are some flares. We've got our complement going off. So there is an immune response, and we send off our antibodies to this. But it's slightly different, and it looks a lot like us. So just for instance, it's producing a protein that looks a lot like C3, like our complement protein C3. Our phagocytes will eat up the bacteria. They quite happily do that. But unbeknownst to our poor B cell and all these missiles that are getting sent out, it's also targeting C3 or targeting the kidney or targeting a protein that is self. This is autoimmunity. We've probably heard of autoimmunity. Rheumatoid arthritis is probably one of the widest known autoimmune diseases. And in this case, say for instance C3 nephritic factor, C3-Neph, that's where antibodies, these missiles, target our own proteins. And they, of course, once they've targeted those proteins, they don't know that they're not doing the job that they're supposed to be doing. The phagocyte doesn't know either. He just comes in and starts causing mayhem in the kidney. So, and that's one potential, this mistaken identity, is one potential way that the immune system can turn against us and cause autoimmunity. And that could be any protein within the body. And the different autoimmune diseases we have are when the immune system targets a different organ or protein. Right. So there he goes, finished. MPGN, C3 Glomerulopathy, is inflammation, or just to break it down, on fire, essentially. That's what it means. It's heat and burning up, and you do get that. So MPGN falls into this territory. It may have a lot to do with B and T cells going off track. We certainly know that antibodies are involved in many aspects of MPGN, and certainly antibodies to complement proteins, which is something that I work on, are involved in creating the conditions that lead to the immune system losing its balance and beginning to see this as potentially foreign. Sometimes we attack ourselves. In a war, things can get out of hand, and we end up attacking self. So in this case, we have lots of complement, we have lots of these flares, and then potentially the immune system can see these flares, this complement, as actually being the enemy, and they start to attack the enemy, and that enemy turns out to be self, and it becomes a bit of a mess. Trying to find out what triggers this is a real challenge because we don't know where amongst this huge complex organization, the huge machine, where it's going wrong. Okay, I'll bring up these guys. Anyone know what these two are? Go on. They are indeed. They're the first ones to be dropped. So this is Little Boy here, which, good naming for an atomic bomb, which was dropped on Hiroshima, and this one is Fat Man on Nagasaki. So these are the original WMD, the weapons of mass destruction. And what I'm trying to illustrate is that once you unleash a weapon like this, like a stealth bomb or dropping a bomb, to clear something, you get a lot of damage around it, and the tissue tries to resolve that. The kidney tries to sort that out. But if sometimes in those processes, you create a lot of damage to the tissue around, and you struggle to bring it back under control. We don't know why all of this happens yet in MPGN. We're working on it. But all the years of knowledge of the immune system has brought us to the point where we can trick the immune system into accepting self. So here we have this is the normal kidney here, and this is also a normal kidney, but it just happens to come from someone else. We've matched it as closely as possible. Here we go. It's nearly the same color. But the immune system is still going to recognize that as foreign. But we know what's going to happen, so we can intervene with drugs. So we can now switch the immune system off, so we can try and get rid of that. That helps to get rid of our dendritic cell involvement, and in doing so, that reduces the T cell involvement, and so on. And eventually, we've switched it all down. We are doing this across the body to a large extent, so we are open to infection a little bit. But in doing that, we're able to put a kidney in here that may last your life if it works really well, if we get this immune system. And the immune system will start to eventually treat this itself. So these are the things that I wanted to talk about. I may have blasted through it a little, but day in and day out, the immune system does keep you healthy. But sometimes, when it's doing its job, it can get carried away and it can cause collateral damage. Sometimes it confuses friend with foe, so we have autoimmunity. We generate antibodies to self, such as C3 and that leads to direct and collateral damage, all rolled together. We don't really understand why such failures occur. They are probably manifold, and we're all individuals. We all have a slightly different way of dealing with the world, both in a personal way and in terms of the immune system. So for everyone, the immune system is different, and so sometimes they are hyper-responsive. I mean, I'm dealing with allergies at the moment. That's a form of inflammation. My immune system is just too good at its job and is now targeting pollen as an enemy, which is the wrong thing. And in a way, of course, I'm lucky it's just pollen, but that is similar sorts of things that are going on in MPGN. We don't know why it's working, but we're working hard to understand how the immune system fits together. That's what got me interested. Of course, I did want to be a fighter pilot at first, but I've set off and I'm doing something which I considered is probably more worthwhile, trying to work out how this all fits together, trying to come up with ways of making it better, and maybe ultimately ways to stop it from happening in the first place. And I'll leave you a picture of where I live, or at least a view from close to where I live. This is the North Sea coast, which is a beautiful place to live close to. I don't quite live just on there, but yeah. Thank you for listening to me yappering on, and if there's any questions, I'll be happy to try and answer them.
Well, thanks very much, Kevin, for explaining the immune system's version of shock and awe. And if anybody wants to ask Kevin any questions about aircraft recognition, or indeed the immune system, now's the time.
Yeah, please.
You have so many things on the market for people to boost your immune system.
Yeah.
If we were to buy things on the market to boost our immune system, would that make it worse? Or do these things just not work?
Well, it depends what you mean. I mean, things like zinc and basic things will boost the immune system. It's a very complex picture. It depends what they were boosting, and you know, one compound, regardless of what it is, cannot boost the entire immune system. So in essence, I would be wary, but the only way to do it as a scientist, you would say, would be to test it. But yeah, I mean, there's no easy answer to that question. I would probably stay away from things to boost the immune system, because we don't know exactly what's going wrong in the immune system in these conditions.
Right. Okay, thank you.
Thank you for that talk. It was fantastic. Is it genetic? Can you answer that?
There's got to be a genetic component. That's what makes us who we are, in essence. I mean, obviously there's a genetic component to the disease. There probably and likely will be an environmental component. So that would be possibly the kind of bacteria you've been exposed to, the kind of chemicals you eat. Anything like that may have a role in precipitating the disease within an individual. Genetics is obviously important, and I'm sure we'll hear lots about that later on today. But it will be a combination. And we don't know what the exact mixture of that combination is. It could be that a virus, a bacteria, one of those many pathogens, helps to break down that balance. But it may not be. It may just be a combination of things that come together from your genetic makeup, from the way that you see the world, from the way that you see self. All of these things interplay. So the short answer is yes. Yes. I think I think there's evidence that it could be involved in these, again, in the loss of the balance between self and non-self and tricking the immune system. There is some evidence there. That hasn't completely firmed up, but there's enough evidence to make me interested in it. There's one over here. There's two.
Thank you for your presentation. It was very entertaining and quite simplified way of explaining immune system. My question, can it be reprogrammed? Are you working on something which...
I think the answer is yes, it can be reprogrammed. Understanding exactly, or finding the right control mechanisms to do that, yes, I think that can be done. And in a way, that's what we do try to do with therapies, is to because it's a chain of events that lead to the loss of control. And if we can find the right ways of slowing that or bringing that loss of control back into control, then that's in a way the ideal therapy. We bring it under control. We don't want to wipe out our immune system or the complement system for that matter. We do want to bring it under control in a way that allows us to defend ourselves against all these pathogens, but not attack self. So in essence, yes, and if you know what that is, then please tell me. But it's that kind of thing, and yeah, we do work towards that, the genetics element of that, trying to work out what potentially is going wrong. That if we could just put a protein back into the system, into the immune system, that may be missing, but we don't know. If we could do that, then it may bring it all back into balance. There are things like the cytokines, where some of those that are naturally produced may have roles that we could exploit, and there are proteins in our bodies that we haven't found yet. So yeah, I think yes, we could bring it back under control. Will it happen soon? Unfortunately, probably not.
That's it. And that concludes the first session. We can now have coffee, and as I say, we're quite happy to be approached to discuss anything you might have heard. Thank you.